Hi everyone. Well, today we'll talk about the automation of K8s clusters and rapid DevOps. This will be divided into three parts. After introducing myself here, I will later demonstrate with code and real scenarios. Alright, the first part is about rapid setup and troubleshooting, and then the one-click setup of a local Kubernetes containerized development cluster. In a microservices architecture, the most challenging part for newcomers is setting up the environment. We have more than a dozen services such as ELK, Kafka, Redis, and various other components. In the past, just getting it running would take 2 to 3 days, so I designed an automated script for this. Now, newcomers only need to run this script, and it will automatically handle pulling Docker images. It sets up the K8s cluster, including building infrastructure like Ingress and metric server within K8s. Once completed, it will automatically set up Redis, MySQL, Kafka, and establish some internal cluster connections. Then it sets up and launches the entire monitoring and alert system, as well as CICD systems like Argo CD, etc. Finally, it starts all the microservices, and within 10 minutes, we have a complete local K8s containerized development cluster. This cuts down the onboarding time by 90%. The second part will introduce ADE direct connection to K8s breakpoint debugging. Once the environment is up and running, the development experience becomes the focus. Previously, debugging microservices locally was difficult because we could not directly connect to services within the K8s cluster. So I integrated a tool called Telepresence, which is currently maintained by a fairly authoritative organization. It allows IDEs to connect directly to the K8s cluster, enabling developers to start services in their local IDE, intercept, and receive traffic from within the K8s cluster. This means we can set breakpoints locally and debug the environment's traffic directly, solving the pain point of difficult local debugging for microservices. It makes the development experience as smooth as writing monolithic applications, saving us the time of deploying to the Devi environment after each adjustment. The second part will introduce environment consistency and collaboration. We previously addressed the issues of setup and development debugging. Here, I also address the issue of configuration fragmentation. Previously, we would use localhost locally and K8s domain names online. Development, testing, and staging environments might each have their own domain names, requiring multiple configuration files, which easily led to errors. I used Core DNS and Ingress to simulate and install a complete K8s DNS environment locally. Now, whether it's local development, online operation, or any environment, service calls are unified with the same domain name. We've achieved write once, run anywhere, with unified configuration, eliminating the maintenance cost due to environmental differences and the need for deployment and operational communication on service architecture and configuration. The operations team now governs all environments with a single configuration. The second part will introduce environment isolation. This local cluster is not only for backend use, but also serves the front end and testing. By configuring ingress rules, front-end and QA colleagues can directly connect to my local K8s cluster for integration testing. This means that every developer's computer is essentially an independent integration testing environment. Front-end no longer needs to queue up for shared DDEB environment updates, and they can also set debug breakpoints locally. The testing team no longer needs to coordinate environment usage or deployment versions and can conduct efficient point-to-point integration testing with the backend anytime. This resolves team bottlenecks and significantly reduces communication costs. Finally, we have the intelligent CICD. Previously, for every small change, we had to remember which services were modified and then find and deploy each corresponding service in Jenkins one by one. It was very time-consuming. So I optimized the GitOps process, implemented code change policies, and change detection mechanisms. The script will automatically analyze the Git diff to accurately identify the changes made to the current card, branch, and modified modules. For example, if we only modified order and account, then Papaly will automatically build and deploy order and account. This achieves precise deployment. This eliminates the need for capability assessment and increases build efficiency by at least 70%. To briefly summarize, I utilized automated K8s cluster setup and rapid DevOps integration, including a 10-minute quick setup. With direct IDE debugging, unified configuration, environment isolation, and intelligent CI/CD, a complete DevOps cycle is constructed. This liberates the development team from tedious maintenance tasks, allowing them to focus on business code. Now I'll look at the first part, examine the code, and demonstrate the entire process, along with an explanation. I've initialized the entire environment, and currently this operating system only has Docker installed. The Kubernetes is not set up yet. Then, once a newcomer joins, they can first set up their K8s cluster. They can use Kite or any other tool. For convenience, I'll use Dast, Take That, and Desktop directly. Here you can choose to use Kite to set up a cluster with one node. Create it. Okay, wait for it to finish setting up. It should be done in one go. Okay, setup complete. Now let's execute the script within the project. Inside this project, in the scripts folder, there's a script called blastup.sh. Let's run it. Okay, the script will now automatically set up the entire K8s local containerized development environment. It will perform several actions. Initially, it will pull all Docker images, which is done serially. This is because Docker has network speed limitations. After pulling the images, your first execution here might be slow because pulling an image takes some time, but I've pre-pulled them already. In the second part, it starts setting up the infrastructure, including the metric server, ingress within K8s, and then MySQL, Redis, and Kafka. It will also automatically establish the connection and election mechanisms for the Redis cluster, Kafka, as well as for Nacos, Acos, and Agos CD. Once set up, the development environment will have a complete server setup that allows for local development, including CI/CD, a full suite of alerting and monitoring features, and a Grafana dashboard. This facilitates developers in using the Grafana dashboard for local experiments. In this part, all processes are handled in parallel to speed up processing time. For example, when Kafka is building its cluster, other threads can handle different tasks. Each concurrent process's logs can be viewed here. You can see each process's status and real-time logs here, which is helpful for debugging later, as individual environments may have some inconsistencies. If issues arise, you can view the logs here, perform simple troubleshooting, and then modify the scripts accordingly. Okay, let's wait for it to complete execution. Okay, After all the clusters are set up, once the infrastructure is established, it will deploy your application containers, such as services like Exchange. This will all be handled in parallel at this step. Then it will finally list the status of all the pods. You see, all are running, but the Exchange here has failed. The reason for this failure is that these images haven't yet been added to K8s. We must do this when we later introduce CICD. We need to push the code up, then have CICD pull in the latest image and deploy it as a container for execution. The situation is broken. Then finally, it will list all the services here, including the domain names for Ingress, MySQL, Redis, Kafka, and all these services. And the login credentials. The usernames and passwords are listed because, for example, Agog might have random passwords each time, and checking them yourself would be cumbersome, so it's all organized here. The entire script took 130 seconds to execute for the first time. Okay, now that everything has been executed, I need to set up a connection to route the DNS in K8s to this OS, so I can connect directly. Now I'll start here. I'm now using the tool mentioned earlier, which everyone can download. And the first time you use it, you need to execute this command. It will install some related tools into K8s. Okay, installation complete, then proceed to connect. Okay, connected. Now let's conduct a test first. Oh, not connected yet. Hold on a moment. Okay, connected. Now let's test. For example, now locally connecting here, I should be able to see Prometheus. We have it, and then all the infrastructure. This is the first time Argo CD is being run, okay? Argo CD is ready now. Then we'll test the MySQL connection and incidentally create tables in it. Later, I will start services locally and test the IDE. I want to test the IDE's direct connection to K8s for debugging. So now I need to connect to MySQL and create tables in it. Hold on a moment, there's a cache here, I'll clear it first. Now creating a schema. This is the table I'll need when I start the service in a moment. This one was answered incorrectly. Okay, now I'll look for the script. You can do it when creating the table. Here. Find the initialization script here. Okay, the table is created. Now I'll open the IDE. I'm now going to start running these services locally. For example, I guess everything has started up. Wait for it to start processing over there. All right, let it run for a bit. It's fine. Now I'll demonstrate setting a breakpoint. First, I go to the order service, the controller here. I'll set a breakpoint when creating an order here. I'll go in first and set a breakpoint. Okay, now I'll trigger it by starting the front-end server. Okay, the front-end server is configured and started, so now I have a local front-end page. Let's check the port. 1,234, 51,735,173. The front-end server took a bit to start, so now I'll begin placing an order to trigger the breakpoint. Okay, I'll proceed with placing an order. The order can be placed. All right, the breakpoint has been triggered. It hit this interface, and now the breakpoint here has been triggered. We can now promptly proceed to connect to the K8s cluster for breakpoint development. Okay. Now let's add some supplementary information. First, let's take a look. Right? All right, these are all the pods currently running in K8s. And for the memory usage part, because local development has limited memory, if it's too high, there will always be swapping and the computer will become slow. So I configured some resource saving measures. The total usage probably doesn't exceed that. This needs to be calculated. It should be around 6 to 7 gigabytes. All right, or perhaps a bit lower. So locally, the cluster's load isn't too great. A typical 32 gigabyte computer is more than enough to handle such a development environment. Okay, let's add a second piece of information here. Within this cluster, there is MySQL, two groups that serve as each other's backups. And then there's a Redis cluster and a Kafka cluster. Additionally, it has a Kafka connector, which automatically subscribes to the bin log of MySQL and replicates it into Kafka's topic. Also, there's the Red Panda console, a very useful tool for understanding all aspects of Kafka, and it deals with topics and consumers. A lot of control is done. It also has a complete set of monitoring and alerts. Right, and it also has its own front-end server. So this is very useful for development as you have an independent environment and a complete set of servers. It makes it convenient for you to perform any tests and to modify any configurations for debugging. Okay, so this is an independent development environment, a rapid setup process, and the actual development entity. The second part is about introducing consistency and collaboration in the environment. In our daily development, a major issue for the development team is the gap between the development team and the operations team. For the development team, the internal network architecture managed by the operations team is often a complete black box. So the development team will set up their own Docker Compose environment and configure various startup parameters themselves. Then they start their experiments, operate in this environment, and once the experiment works fine, the operations team migrates this network architecture during deployment. Then they map some scripts or startup parameters we made into K8s, configuring them one by one. This process can actually be simplified. In our current architecture, we no longer need Docker Compose, just K8s. The second part is about configuration unification. In the past, each environment needed its own configuration, which led to redundant configurations. Managing and operating them, those small tasks, become cumbersome and time-consuming when accumulated. Okay, let's look at the code first. Now we do not need Docker Compose anymore, just K8s. So the operations team can directly adopt and use the network architecture employed by the development team. So these configurations and these some sequence passwords, config, all of these can be used. And including some scripts for Redis cluster connections and Kafka cluster connections can be directly applied. The only thing the operations team needs to do during deployment is configuring for persistence, resource limits, and some specifications. Make additional configurations. However, in the overall architecture of K8s, it can almost be directly applied, only needing to distinguish some details by environment. The second part is about looking at services. Now you can see for a service like Exchange account, its configuration is actually minimal, almost requiring no management. So when you create a new service, you don't need to configure much, just change the basics like the service name here. The reason configurations are so streamlined is because I used SDK for preset configurations, such as MySQL, Redis, Kafka, and Spring MVC, Spring Cloud. For MySQL, in its configuration, it has already been set up a dual master configuration for sharding and some database connection parameter configurations. In other words, all MySQL configurations for microservices are uniformly applied here. If individual services have certain differences, you can configure the same parts to override the settings here. This configuration will be used across all environments. So the reason this can be done is that each server's domain name, now all environments use the same K8s, it's unified. And password inputs are also read from K8s. So this can greatly simplify the configuration. It also reduces a lot of manual operations. This also lowers costs. Let's first introduce environment isolation. In daily development, sometimes there's only one development environment, and when debugging, everyone needs to coordinate their versions, perform merges, and handle conflicts. This can actually take up several tens of minutes in a day, or even more. Sometimes asking the operations team to set up an additional environment can be troublesome. Setting up a large environment takes a longer time, and for them, it also requires, it takes up some working hours. It's a task that takes time. The second part is when the testing team is conducting tests. To avoid being affected, they may set up several testing environments for multiple testing teams. They need to communicate about who is using which environment, which testing environment. They need to clarify who will use which testing environment. And when a problem occurs, developers need to ask each other which testing environment they're currently using. Then find each server of that environment one by one to investigate. Uh, this whole process is rather complex. Now, with this system, each developer has their own environment. And this environment already includes the front-end part. So for testing, it can directly connect to the developer's computer for testing. If there's an issue, the developer can directly check the logs and set breakpoints. Besides setting breakpoints directly, another advantage is that for developers, they work within the same environment from start to finish. They don't have to worry about which environment's library they're working on, what the location of that library is. No need to do these distracting tasks anymore. Yes, so the second advantage is environment isolation. Because it's a completely isolated environment, it won't be affected by anyone, preventing your work from being in vain. There's no need to communicate with others about the current version, merging code, or conflict resolution. These are the benefits of environment isolation. Finally, a supplement here is that when using this process on Windows, you need to pay attention to the integration issue between Docker, WSL, and Windows. Now let's open my WSL configuration file. This is my WSL configuration file, which you can refer to if you want to use this process on Windows. The most important thing is your network. The network mode should be set to this because Telepresence might have some internal issues if you don't use this mode. You'll probably encounter this situation. After interacting with K8s a few times, there will be many error logs in your Docker container. They are related to the network. Everyone can refer to this configuration and enlarge it a bit. The second thing to pay attention to is if you find that during development, the services within the K8s cluster, if it's very slow or unresponsive, you need to check your Docker container here. Then check if the write volume is elevated. If it is, it's likely caused by the virtual memory swap. Then you might need to reset your WSL and restart everything, which will temporarily restore it to normal. To address the root cause, you need to further reduce the memory consumption of all your services. Then observe and see if there are no issues. It should be fine, but if your memory is too saturated, it will start swapping and your I/O will spike. After the I/O spikes, all services will stop responding. The last potential issue is that suddenly all services are unresponsive or respond very slowly, and this happens to all services within K8s. And on the Docker container side, hundreds of MB are being written every second, which also seems to be an I/O issue. At this time, you can check the pod traffic manager in K8s. This is a service installed in K8s by Telepresence. Then it will periodically establish a connection heartbeat with our client. For some reason, if the connection fails or can't be established, Traffic Manager will keep retrying. If you look at the logs inside Traffic Manager, you will see logs being printed repeatedly, and each time they are printed, K8s will inevitably write input, output, causing your service to crash. At this point, the only solution is to kill the port to let it restart, which will resolve the issue. This problem is difficult to identify how it occurs, but once it happens, it can cause some trouble. Before, I always rebooted, but later I found that killing the pod solved the problem. Now let's look at the last part, intelligent CICD. This part is about, for example, if I change 3 services in this code update, when deploying the code, the CHD process will automatically detect which 3 services I changed and automatically deploy the code for these services. Okay, let's demonstrate now. This time I'm using CICD with Git Asia connected to Argo CD. So the CR script used by Git action can be seen here, where some necessary configurations need to be done, and below is the content of the script. Okay, now I'll directly demonstrate the CI/CD operation process. Now there are 2 services, service template and service test. Here the suffix is a number, all 0. Okay, now I'll change the code. Change it to 1. Hamid. Now I'm pushing this code to Git. Okay. Then Git Asia has already received the code and it's running now. I want to click in to check. In the first stage, it will analyze which modules have had code changes. After changes are made, it will compile, package, and create images for the 2 modules that were changed. Let's wait a moment. It takes about a minute. Here you can click to see the details, specifically service test and service template and service test, these 2 services. It compiles and packages concurrently, so the speed is relatively faster. Okay, now it's done. Let's look at dikes. Now I'm switching to another repository, the GitOps repository, where I can pull the latest changes to see them. Okay, this is the change from git test and
Git template
change. They are directly updated in the K8s YAML file written here, and the timing is consistent. Then in AGOCT, it will automatically detect the change. Yes, wait a moment, it has detected the change and automatically deploys it to the local K8s cluster based on the YAML file. Okay, let's wait for it to finish deploying. Okay, deployment is complete. The suffix we just saw was 0. Let's refresh it again. Just a moment. Okay, it's changed to 1. The template is also 0. Refresh it. Okay, everything is updated. So that's my demonstration. After you push the branch, it will automatically detect which services have changed, package them, and then deploy.